So I'm working through some of the equipment I've got here, and I've come across, or come into this one here, and I need to calibrate this thing. It's a Vector display. You can see there, it's a CRT, and I need to power this thing up outside of the unit that it's installed in. It's actually installed in a 4145A semiconductor parameter analyzer, and I've recently picked up a 4145B, the newer model. The A and the B are pretty much the same. They've just got a 5.5 inch or a 3.25 inch floppy drive between the two. Like the newer one's got the smaller, more common floppy drive. But I need to power this thing up outside the unit so I can tweak all of the settings. There's heaps of them all over the place. There's some inside here as well and all that. And you can't calibrate this thing and set it all up while it's plugged in, because you just can't access all the dials you need. So this one actually had a focus issue, and I need to I've replaced a couple of parts, and I just need to power it up. So I thought, well, jury-rigging it up with my benchtop power supplies is a little bit dicey with alligator clips and stuff. So I want to make a dedicated power supply so I can calibrate these things. I've got two of them now, and I thought it would be worth just a bit of fun, make a power supply and get these things powered up on the bench, and I can tweak dials to my heart's content. Now, I had a bit of a setback because the original design was going to use a switch mode power supply. This is the offending article here. And then the output needs to be a very low ripple. The specifications that HP make for their this Vector display is like 10 millivolts on each rail. It needs 3 voltage rails, a 5 volt, plus 15 and minus 15, and it wants like 10 millivolts of ripple, which is quite low, especially for a switch mode power supply. This is good for like 20 or 30 millivolts a ripple or something. So I was going to team it up with a little filter board that I made, some inductors and capacitors, to then give me that low ripple. This is made by PCB, the usual sponsor for this channel, and they've done a fantastic job. The circuit board is great. The quality is, as usual, completely fantastic, basically perfect. And yeah, it doesn't work. The board is fine. There's nothing wrong with the production of the board, but this is no good. I can't use it. It puts out the 5 volts and the plus 15, or the plus 5, plus 15 and negative 15 volts. That's fine. But when I load up the rails, the 15 volts and the plus 15 and negative 15 volts drift all over the place, because every output is referenced to the 5 volts. So you imagine you've got no load, and the 5 volts is 5 volts, and you start putting a load on there, and because of voltage drop and losses and stuff in the power supply and the cables and all that, the voltage drops. So the power supply goes, oh, we're not at 5 volts anymore, let's bump that voltage up, let's trim it up until we get 5 volts. That's fine, that works perfectly. The 5 volts is nice and stable. The problem is the 15 volt rails, the two 15 volt rails, are referenced to the 5 volts, so they go up. And when you take the load off the 5 volt rail, it goes, oh, now the voltage is too high, so let's trim that back down. And then the 15 volt rails then drop down. They vary by as low. I've seen them as low as 14 volts and as high as 16.5 volts, depending on the load on the 5 volt rail, which is completely and utterly useless. That's 2.5 volts drift up and down on those 15 volt rails, and I can't have that with this thing. This thing needs, according to the specifications in the HP manual, it needs to be much, much tighter than that. I can't deal with like 2.5 volts up and down. So, especially when I'm trying to calibrate something, I need the rails to be spot on, so I know when I calibrate it, it's calibrated correctly. It's not going to be out of whack because of voltage drift. So this thing, the RPT-60C 3-rail switch mode power supply by Meanwell, which Meanwell usually make really good stuff. In this case, this is, for my application, complete and utter unusable crap. So that's going away. This is going away. I can't use it. Instead, I'm going to brute force it, because I just got to get these things finished. So rather than faff around and try and figure out some really elegant solution, I'm going to go linear power supply. So I've got this circuit board here, and it's got 3 linear regulators, and that's going to give me my voltage. Now, This project will be revisited in the future because I do want to improve it. But for now, we're going to focus on the production of this, and I'm going to explain how to build these circuits and how to spec the circuits to get the required voltage, because they are a very useful design. These regulators that I'm using here, they're usually just common jelly bean parts. But yeah, I'll talk about how to get from I want this voltage to a working circuit in this video. So that's going to be the regulator, and then I've got the enclosure here. So our front panel is going to have 3 LEDs, one for each voltage, to show us that we got our 3 voltages. And then in here we're going to have just a 4-pin Canon jack, and that plugs into our circuit board, and that gives us our output there. And I'm going to have a cable that comes out and plugs into the Vector display. We've got our IC socket fused and switch and mains filter and all that, so that's all integrated. Really handy little block. And transformers. This is the brute force part of it. I'm using 1 transformer per rail, which is completely and utterly overkill, and I know it's ridiculous, but I've got to get this done, so I'm just doing this for now. The revisiting will be replacing this with switch mode. Okay, so here's the schematic. You can see there's 3 main sections, one for each voltage rail: the positive 5 volt, negative 15, and positive 15. The only difference between these is that the negative 15 volt uses an LM337 instead of the LM317 of the other 2 positive rails. All that means is that you need to flip around your bridge rectifier and your capacitors, and also your protection diodes, because it's a negative voltage, so you've got to reverse the polarity of everything. But the actual selection of components is exactly the same. It makes no difference. So let's have a look at the 5 volt side, just because, and see what we've got here. So on the left we've got the input jack, the input plug on the circuit board. That's our AC coming into the full bridge rectifier. That then feeds through into the voltage in of the LM317. Before that though, we've got a 0.1 microfarad here. That's specified by the data sheet, so I stuck it in. Just a bit of decoupling and a bit of filtering. But first we need a 1000 microfarad here, because the DC coming out of the bridge rectifier is actually pulsed. It's like a very full of ripple. This capacitor smooths that off, so we get a nice smooth DC coming in. Once it comes through here, it gets regulated. It comes out through a polyfuse, which I've put here, and then out through this line to the front panel jack. There's a connector here, which is going to the front panel LED, and the usual just current limiting resistor there. Nothing special, just a LED and a resistor. So we've got a output filtering capacitor there. Does a little bit of filtering, bit of bulk capacitance, so that if there's any load transients, it can fill in, and we don't get any little voltage drops. And then in the middle is where all the magic happens. So we'll work to these resistors in a moment, but first of all, because we've got output capacitance and your load might have a capacitance, this is something I'm going to plug in, so I could have, I could use it for other purposes and whatnot. I need to put this diode here in. That's so that if any capacitance on the output side of things, including this one here, discharge when you turn the power supply off, it'll try and discharge through the LM317, which is no good. That can damage the LM317, it damage the regulator, and cause problems. So this just gives a path for the capacitor to discharge, so that you don't end up blowing up your regulator. Down here at C12, this 10 microfarad down here, that is there to improve ripple rejection. Basically, it prevents the amplification of the ripple as your output voltage increases. It just makes for a more stable output and a much cleaner output too. So if you put that in, you also need this diode here as well, so you can discharge properly and not cause any problems as well. So coming along to these resistors, this resistor here, R10, this will always be 240 ohms. In 99.9% of applications, you're going to have that as a 240 ohm resistor. That's the fixed one. Down here is what you vary to vary your output. So normally you have one resistor and you just set that to what it has to be, and then you get your set output. But because I want to trim this up and get it just spot on, I've put the variable resistor in. Now, if you were building a little linear power supply that you wanted to vary the output like by a wide range, you wouldn't bother with this one. You just have a variable resistor that's set to the center scale of that variable resistor is to your nominal voltage, say 5 volts or 12 volts or whatever. And then you can vary that all the way up and all the way down to where you want to go. Or you might have it set so that when this dial is set to this maximum, that's set to 12 volts, and then you can wind it all the way down below that, depending on the application. But because I want it set to 5 volts, but I still want to have a trimmer there, I've got the variable resistor here, and I've put this one in here to expand the scale of this one. So in my circuit, I needed roughly 750 ohms or so. So I've gone, well, I don't want to waste the whole range of my potentiometer when I'm only going to be dialing in a small amount. It also makes it a little bit more difficult because when you're turning the resistor, if your adjustment is only on like 5% or 10% of that variable resistor, you make one little turn and it can change the voltage by quite a bit. But by expanding the scale of that resistor, you turn it a little bit and the voltage changes a little bit, and you turn the dial a little bit more and it only changes a little bit more. So you can really get an accurate and precise adjustment going on there. So what I've done is I've gone, okay, so I need 750 ohms roughly. So let's just like ballpark it, what feels good, about a 500 ohm resistor. I've written 500 ohm there, but I think the standard value is about 510 or something like that. It doesn't matter. So I've put that resistor there, and then so that's 500 ohms of my 750. Now I've got 250 ohms I need to add to that. So if I want my variable resistor to be center scale at the calculated roughly 5 volts, well, 250 ohms plus 250 ohms, that's a 500 ohm resistor, because at center scale, you're going to be reading half up one way and half down the other of your resistance. So a 500 ohm resistor there works quite well, and it turns out I can dial that into like a hundredth of a volt, and it's stable like that. So that worked out quite well. So that's what I've done there. And then if we come down to here, I needed a 2.5k roughly, maybe 2.4, 2.5ish k. So I've gone, okay, what's a good rule of thumb? Like not rule of thumb, but a good, feels good number. 2k resistor, and then I've got 500 ohms left over because I need 2.5k. And then so I go 5 times 2, so 500 ohms plus 500 ohms, either side of the center scale, 1k variable resistor. And that worked quite well too. So that there is how the regulator works. And then of course each one of them comes all the way out to our output connector there. And here we are with the finished PCBs, sponsored by PCBaway of course. Fantastic quality as usual, not a problem at all. And they do have promotions on all the time, so check out their website, because you always find something going on. Get some free PCBs or some free credits or something. Submit your ideas, submit your designs, and yeah, there's always a competition or a promotion going on. Check them out; they do make some good stuff. So I think it's time to get these things populated. So I don't know about you, but buckle up. I feel a time lapse coming on. Okay, so I haven't put the regulators in, and there's a very good reason for that. They actually have to come through the bottom of the board and then screw down to the aluminium chassis, as the whole chassis is going to be a heatsink. But if I put them in and then screw it all down, there's no way I can get the legs the right distance from the board, and that's going to cause problems, because when I screw that down, if the legs are too long or too short, if they're too long, it's going to crush down and put stress on the legs and on the solder joints and whatnot. And if they're too short, when I put the screw in the tab there, that's going to pull down and do the same thing. There's going to be stress on the tab, on the legs where they exit the case, and on the solder joints, and that's going to cause things to crack and just generally have a bad time. So it's very important that when you have something like a regulator or a MOSFET or a transistor or something screwed to the chassis that's separate from the circuit board, you do that solder joint last. So what I'm going to do is I've got some sill pads. I want to put a sill pad down, then screw this one down, same with the other two. These legs will be bent 90 degrees upwards, and when I drop this circuit board on, they'll come up through the holes. Then I'm going to screw the circuit board down, then solder it. That way, where I solder those legs in is going to be the perfect distance, and there's going to be no stress on those legs or on the package, and that way it won't crack. And that way, even if I undo the screws and take the whole lot out with these still attached, they're going to remain in the same position, and then I can put it back in. It's perfect, and it's not going to be any problems. Okay, so you can see we've got the circuit board in there, all nicely screwed in and tight. The three regulators are there, sill pads and all that sort of gear, so they're nice and tight, but they're not soldered in. So those legs are actually just free floating in the hole. So if we go ahead and solder that in, I'll just do the middle one to start with. Then those solder joins, because it's all been pre-positioned, are not providing any stress whatsoever onto that part. So that's perfect. And like I said before, if I go and remove this and put it back in, that's still going to be in the perfect position. So that is fine, not a problem whatsoever. So I'll go ahead and do the other two, and then we'll get the transformers installed and put it together, leave the lid off, and we can turn it on and see how it runs, and trim those trimmers up, the trimmer resistors, and yeah, hopefully we get a good output. So there we are, all put together. We've got our brute force 3 transformers here, which, as I mentioned before, will be replaced with a switch moody setup, make it more efficient and more lightweight and whatnot. They feed into the regulator board, which is sitting here thanks to PCBWay. 3 regulators bolted down as described before. They've been installed with sill pads and insulator washers just to keep them isolated from the case, so there's no weird like backfeedy kind of ground loopy sort of stuff. Then we got the 3 blue bits are the trim pots, so we can just twiddle those with our tongue in the right position and get the output voltage correct. Comes out of here to the front panel, and then we've got our 3 LEDs, of course, for showing what voltage. The front panel you see is like nice and shiny. I use this paper, like inkjet printer paper. It's like a plasticky sticker, and you can print on it. And then they also give you a clear sticker that you laminate over the top to make sure it can't scratch off again. And it ends up looking real good. It looks like a like silver paint kind of effect, but it looks really, really nice there. Just a basic design on this one. I didn't spend any time on the design there. But yeah, on the back as well, same thing. Fuse size, I've got the output pin out for the output connector, and the input voltage on the bottom there. So that is going to look quite nice. So let's plug it in, and let's see what we get. I've already had a bit of a tweak on the dials just to make sure it's all working and stuff, and it seems to be alright. So if we turn that on, beep, 3 green LEDs, fantastic. That means we've got our voltages. And if I grab my multimeter, I've labelled the circuit board with the output voltages, so that makes it easy. Common there. Okay, plus 15 volts, 15.4, negative 15 is going to be, what do we got? Negative 15.2, and 5 volts is at 6 volts. They're a little bit different, a little bit out because I adjusted it with the device plugged in, so when you load it up, the voltage is going to drift a little bit. But once I plug this in, the vector display, that should make these pull into spec once it's loaded up. Alright, so plug the cable in into the front panel jack there. Got a bit of a funny looking plug here, but you can still buy these. And that will go in the back. I have to be careful because it's going to be all high voltage on this side. So let me just grab it without touching too much stuff. Okay, I'll let that warm up. And let's see what our output voltages are now. So our positive 15 is 15.1. That's good. Negative 15, 14.92. I might bring that up just a little bit. And 5 volts is exactly 5 volts. So that is good. So negative 15. Let's give that a little bit of adjustment. Let me swap hands here. Nine, 14.9, negative 15, just go up a little bit, just give it a bit of headroom. 15.1 might do it. Yeah, that'll do. So that is good. Now let's have a look at what the screen says. Now this isn't actually working correctly at the moment. It's a little bit blurry. It's actually the fault is there was a problem with the focus circuit. But if I turn the lights out, look at that, it's operating. A little bit blurry as I said, but that is fantastic. So that means I can now more easily power this thing up without having like alligator clips and stuff into the power supply board on the back there, you know, wiggling around and stuff. I just plug it in and I can just twiddle away and do my work, and I don't have to worry about having power supply wires falling off and shorting out and stuff. So I'll unplug that because I don't want to touch the high voltage. I'll turn that so the high voltage is down against the desk. That is done. So last step is to put the lid on and then put the screws in. Fantastic. I'll put screws in the sides, and that power supply for now is finished. So that is how you make yourself a linear power supply. Special thanks, of course, to PCBWay for sponsoring the video, and check out their website. They've always got promotions and stuff going on. So yeah, hope you found that interesting, somewhat informative. We'll see you in the next one.